Hello there. In this video we're going to talk about an application of Taylor series, namely how to use Taylor series to find the exact value of particular types of definite integrals. In particular, we'll be looking at the definite integral, the integral from 0 to 1 of the natural log of 1 minus x times x to the n minus 1 dx, where n, say, is a natural number. So to begin our discussion of how to evaluate this integral, let's first off discuss, some of the methods that you might want to even try for this type of approach. You may want to use a u substitution, where u is the natural log of x. You may want to use integration by parts, with that same exact u and the remainder part as dv. But you may realize that if you try either one of those methods, you may get a slightly more complicated integral to deal with. So what we're going to do is we're going to take advantage of the fact that we know the Taylor series is the natural log of 1 minus x, and then we're going to replace that Taylor series exactly where this natural log lies. So recall, if x belongs to the interval 0, 1, then the Taylor series for the natural log of 1 minus x is equal to the opposite summation from k is equal to 1 to infinity of x to the k divided by k. And in particular, this is going to be true when x is equal to 0 as well. So our integral star, which I'm going to call the integral from 0 to 1 of the natural log of 1 minus x times x to the n minus 1 dx, can be rewritten using this Taylor series expression. So we can rewrite this as the integral from 0 to 1 of the opposite summation from k is equal to 1 to infinity of x to the k divided by k times x to the n minus 1 dx. So notice that this is a summation of k, and this is an integral of x, so one can verify that you can interchange the summations and integrals. Also note that this 1 over k term also is not dependent on x, so we can factor that out as well. So we can rewrite this as the negative summation from k is equal to 1 to infinity of 1 over k times the integral from 0 to 1, so we're still left with the xk and the xn minus 1, so we can combine them into xn plus k minus 1 dx. So for this portion, we can apply a power rule, so add 1 and divide by the new exponent. So that's going to give us the negative summation from k is equal to 1 to infinity of 1 divided by k times x to the n plus k divided by n plus k, evaluated as x goes to 1 and x goes to 0. So we know that as x goes to 0, this entire term is going to disappear, and as x goes to 1, this is going to go to 1, since 1 to any power is going to be 1. So we're just going to be left with this constant on the bottom, n plus k. So we can rewrite this integral as negative sum from k is equal to 1 to infinity of 1 over k times 1 over n plus k. So it's an infinite sum of a product of two fractions. So to evaluate this infinite sum, we're going to try and decompose this product into a sum of two fractions with these denominators k and n plus k. So we're going to assume that there exist constants a and b, such that this summation can be rewritten as the sum from k is equal to 1 to infinity of a divided by k plus b divided by n plus k, so where this expression here is equal to that expression. So let's take a moment to figure out what a and b should be. So 1 over k times n plus k must be equal to a divided by k plus b divided by n plus k. So we can cross multiply both sides by the least common denominator, which is k times n plus k. So that's going to give us the expression 1 is equal to a times n plus k plus b times k. And now we can solve the systems of equations, or we can just plug in values that sort of eliminate the other constant. So we can, for example, let k be equal to 0. So when k is equal to 0, we have 1 is equal to a times m. So we get that a is going to be equal to 1 divided by m. So that's what a is. Now we're going to let k be equal to minus m. So when we let that happen, this a term disappears, and we're going to be left with b times minus m. So from this equation, we get b is equal to negative 1 divided by m. So now we can rewrite our infinite summation. So star is going to be equal to negative sum from k is equal to 1 to infinity of a, which is 1 over n, divided by k, plus b, which is negative 1 over n, divided by n plus k. So both of these terms have a 1 over n term, so I can factor that out. So I can rewrite this as star is equal to negative 1 over n times the sum from k is equal to 1 to infinity of 1 divided by k minus 1 over n plus k. And I'm going to distribute this negative sign and revert the signs of both of these fractions. So this is going to give me star is equal to 1 divided by m times the sum from k is equal to 1 to infinity of 1 divided by n plus k minus 1 over k. Now our goal here is to figure out what this sum is equal to. So we're going to look at a bunch of partial terms and sort of see if anything cancels. So let's look at the first few terms. So star is going to be equal to 1 over n times, so the first term when k is equal to 1, so that's going to be 1 over n plus 1 minus 1 over 1, and then plus 1 over m plus 2 minus 1 over 2, plus 1 over m plus 3 minus 1 over 3, and so on. So from these first three terms, we do not see anything that cancels. So since n is a natural number, eventually k is going to be equal to n. So let's go up to that value and see what's going on there. So eventually we're going to get to the term 1 over n plus m minus 1 over m. So this is the k is equal to n term. And then plus 1 over, so n plus n is 2n, so we're going to add one more to that. So 1 over 2m plus 1 minus 1 over m plus 1, plus 1 over 2m plus 2 minus 1 over m plus 2, plus and so on. So let's look and see what we have going on here. So what do we have? So let's see. I at least see that we have this minus 1 over m plus 1 term, and that's going to cancel out with that. We also have this minus 1 over m plus 2 term, and that's going to cancel out with that. So if we continue on in this fashion, then we should see that all of these leading terms are going to cancel as well if we continue down this process. So if we cancel all of them down, well, what are we going to be left with? We're going to be left with minus 1 over 1, minus 1 over 2, minus 1 over 3, and minus 1 over n. And keep in mind, all these yellow terms, minus 1 over n plus 1, eliminate with the preceding terms of the front fraction. So if that is true, which it is, so we can rewrite this fraction. So star is going to be equal to 1 over m times, so negative 1 over 1, minus 1 over 2, minus 1 over 3, minus dot dot dot, minus 1 over m. So all these fractions are negative, so I can factor out a negative sign out. So I have star is going to be equal to negative 1 over m times 1 plus 1/2 plus 1/3 plus all the way down to 1 over m. And what do we have here? So this is the nth harmonic number, which we sometimes abbreviate, or most of the time, by h sub m. So then we get our result that star is equal to negative 1 over m times the nth harmonic number. And what was star equal to? Well, star was the integral from 0 to 1 of the natural log of 1 minus x times x to the m minus 1 dx. And we've shown that this is equal to negative 1 over m times h sub m, the nth harmonic number, where n is a natural number. So that's a neat little identity, and we'll use this for a later calculation that's going to be useful. But let's just use an example of how to actually use this relationship. So let's assume we want to find the integral from 0 to 1 of x cubed times the natural log of 1 minus x dx. So via this relationship, we're focusing in on n minus 1. So we know 3 is the same as 4 minus 1, so this integral relates to this identity when n is equal to 4. So if that's the case, this is going to be equal to negative 1 over 4 times the fourth harmonic number. And what is that going to be equal to if we actually want the numerical value? So the fourth harmonic number is going to be 1 plus 1/2 plus 1/3 plus 1/4. And we can find that the fourth harmonic number is equal to 25/12. So 25/12. And then once you multiply these fractions together, you find that this integral is going to be equal to negative 25/48. So that's what that integral is equal to. So this is just an example, a particular example of how you can use Taylor series to find the exact value of particular definite integrals if it behaves nicely according to the Taylor series about the function that you actually have. And we've also proven this useful identity that's useful for finding definite integrals on 0 to 1 of monomials times logarithms, or in general polynomials times logarithms. And we see that there is a connection with the harmonic numbers as well. And that's pretty much it for this video. Hope you enjoyed.